Let us begin very quietly with an image rather than a definition. Imagine that you are looking at the edge of a coastline from far above. At first it seems simple enough. It curves, it bends, it separates land from sea. But as you move closer, what looks smooth begins to break into smaller inlets and smaller outcroppings. Then the smaller features themselves reveal still smaller bays, stones, ridges, and tiny irregular boundaries. And if you continue this act of approaching, of magnifying, of looking again and again, the shape does not settle down into the kind of neat simplicity that we often expect from ordinary geometry. This is one of the first feelings that fractals give us. They feel natural because the world is full of shapes like this. Coastlines, clouds, mountain ridges, branching trees, veins and leaves, snowflakes, the layered spirals of Romanesco broccoli, all of these seem to carry structure at more than one scale. But fractals also feel uncanny because they resist the ordinary hope that if we zoom in far enough, the complexity will eventually disappear. Many familiar shapes become simpler under magnification. A circle does not reveal hidden corners when examined more closely. A straight line does not become more twisted when enlarged. Smooth geometry comes down as we look nearer. Fractals do something different. They continue unfolding. They continue presenting detail. They continue suggesting that infinity is present, not merely in the counting of points, and not merely an endless process in time, but in visible form, in texture, in shape itself. And this is one of the deepest reasons why fractals are so memorable. They make infinity feel almost tangible. They do not only tell us that something continues without end. They let us imagine what endlessness might look like if it took on a geometric body. It is worth pausing on that thought. In earlier mathematical settings, infinity may have appeared as an endless list, or an unending sum, or a process that approaches a limit without ever stopping. Here, infinity appears in a different language. It appears through repeated structure. It appears under magnification. It appears as endless refinement. That is the mood in which fractal geometry begins. Now, at the center of this topic, there is one very important idea, and that idea is self-similarity. A shape is called self-similar when the whole resembles its parts. In other words, if you examine a portion of the object, that portion may look like a small version of the whole. Sometimes this resemblance is exact. In a mathematical fractal, a small piece may truly reproduce the same structure as the entire object, just on a reduced scale. Sometimes the resemblance is only approximate. In nature, a branching tree is not exactly the same at every level, but there is still a family resemblance between the large branches, the smaller branches, and the smallest twigs. The same pattern appears again and again, not with perfect rigidity, but with recognizably repeated character. That repetition across scale is the key. A fractal is not merely a complicated shape. Plenty of shapes are complicated. A pile of broken glass may be complicated. A random scribble may be complicated. What gives a fractal its distinctive mathematical character is not just complexity, but organized complexity. It is complexity generated by recurrence. It is structure that comes back. It is pattern that survives magnification. Let us say this again in a slightly different way. Self-similarity means that looking closer does not transport us into a completely unrelated world. Instead, it reveals a new level of the same world. The shape repeats its own style. It echoes itself. It carries a rule or a motif that persists. And that persistent motif is what links fractals to recursion. Recursion is the act of applying the same rule again and again. We begin with something simple. Then we perform an operation on it. Then we perform that same operation on the result. Then again and again and again. Many fractals are not drawn all at once as finished objects. Instead, they are generated by iteration. A rule is repeated. A stage is followed by another stage. The object that interests us most is often not any single finite stage, but the infinite form toward which all the stages point. This should sound familiar, because it connects to one of the great recurring themes in the study of infinity. Very often, the infinite object is understood through finite approximations. We do not grasp infinity by completing an infinite task in practice. We grasp it by understanding the pattern that governs all stages, and by understanding the limit, the enduring structure that remains meaningful as the process continues without bound. So once again, infinity arrives through repetition. Infinity arrives through a rule that does not change, even though the construction continues. Infinity arrives through structure preserved across steps. With that in mind, let us turn to one of the purest examples in all of mathematics, the Cantor set. We begin with the simplest possible geometric object for this purpose, the interval from 0 to 1. Imagine a solid line segment, complete and unbroken. Now remove the open middle third. So what remains are the left third and the right third, with the middle gap taken away. Already the segment has split into two pieces. Now do the same thing again to each remaining piece. From the left segment, remove its middle third. From the right segment, remove its middle third. Now 4 smaller segments remain. Then do it again. Remove the middle third from each of those 4. Then again from each of the 8 that remain. And again forever. This is a remarkably simple rule. Keep what lies on the edges of each surviving interval, and remove the middle third from every interval that remains. At first the construction feels destructive. We are removing, deleting, carving away. The original interval seems to be dissolving. More and more of it disappears. Large pieces go first, then smaller pieces, then still smaller ones. The figure becomes fragmented, delicate, almost dust-like. And yet what remains is not nothing. What remains is the Cantor set. It is worth dwelling on the early stages, because they help the imagination. After the first removal, there are 2 surviving pieces. After the second, there are 4. After the third, there are 8. At each stage, the number of pieces doubles, while each piece becomes shorter. So there is more fragmentation, more separation, more empty space appearing between what survives. The object grows more and more discontinuous in appearance. It becomes a pattern of survivors and gaps, of persistence and absence. But the full Cantor set is not any one of these finite stages. It is the collection of points that survive every stage. If a point is never removed, no matter how far the process continues, then it belongs to the Cantor set. If at some stage it falls into one of the middle thirds that gets deleted, then it does not belong. So the Cantor set is made of points that escape removal forever. That description already gives it a strangely ghostly character. It is defined by survival through an endless process of deletion. It is what remains after infinitely much has been removed. And now the surprises begin. The first surprise is that the Cantor set is uncountable. This can feel almost impossible on first encounter. How can that be? We keep removing intervals. We remove a large middle piece, then more middle pieces, then more still. The set that remains looks extremely thin. It looks sparse. It looks almost negligible. And yet, in terms of cardinality, in terms of how many points it contains in the sense relevant to set theory, it is not merely infinite. It is uncountable. It has too many points to be listed one by one in a sequence. This is a beautiful moment in mathematics because it reminds us that visual thinness is not the same thing as set theoretic smallness. Let us pause and reflect on that. A set may look tiny in one sense and still be enormous in another sense. The Cantor set contains no interval at all, and yet it contains uncountably many points. So when we ask how large a set is, we must ask very carefully, large in what sense? This brings us to another of its important properties. The Cantor set is closed. That means, speaking intuitively, that it contains all of its limit points. If points of the set cluster together and approach some location, that limiting location is still part of the set. The set does not miss its own boundary behavior. It is complete with respect to the accumulation of its points. This closeness matters because the Cantor set, though fragmented, is not loose or incomplete. It is not a collection that leaves behind hidden edge points outside itself. The points that arise as natural limits of points in the set are still included. So despite its broken appearance, it has a kind of logical completeness. It is also nowhere dense. This is another subtle and important idea. To say that it is nowhere dense means, roughly speaking, that it contains no interval. No matter where you look, and no matter how small a stretch of line you choose, the Cantor set does not fill any actual segment of positive length. It sits thinly inside the line. It is present, but never in the form of a full interval. It has points everywhere within its own structure, but it does not contain a chunk of continuous line. So again we have this tension. The set is closed, so it is in a sense complete. It is uncountable, so it is huge in cardinality. But it is nowhere dense, so it is thinly spread. It contains no interval, no solid stretch. And then comes perhaps the most astonishing statement of all: the Cantor set has measure 0. This means that in terms of length, it occupies no length at all. That sentence deserves to be repeated slowly. The Cantor set is uncountable, and yet its total length is 0. Now, to a listener meeting this for the first time, that may sound like a contradiction. How can a set contain uncountably many points and yet have no length? But this is exactly the point at which mathematics teaches us that different notions of size are genuinely different. Cardinality asks how many points a set has, in the sense of whether its elements can be placed in one-to-one correspondence with the elements of another set. Measure asks something quite different. Measure asks about geometric extent. It asks how much space is occupied. It asks about length in 1 dimension, area in 2, volume in 3, and more refined notions in more abstract settings. These are not the same question, and the Cantor set is one of the clearest examples showing that they can separate dramatically. In cardinality, it is vast. In measure, it is negligible. It is worth repeating because this is one of the deepest conceptual lessons in the entire topic. Mathematical size has more than one meaning. A set can be large with respect to one meaning and small with respect to another. The Cantor set is a kind of quiet paradox. Not a contradiction, but a challenge to intuition. It teaches us to become more precise. This is why the Cantor set is not just a curiosity. It is a training ground for mature mathematical thought. Now let us gently move to another classic fractal, the Koch snowflake. If the Cantor set lies on the line and teaches us about removal, thinness, and cardinality, the Koch snowflake lies in the plane and teaches us about boundary, enclosure, and the strange coexistence of finiteness and infiniteness. Begin with an equilateral triangle. Each side is straight and simple. Now focus on one side. Divide it into 3 equal parts. Replace the middle part by 2 sides of a small outward-pointing equilateral bump. So instead of one straight segment, you now have 4 smaller segments arranged in a jagged form. Then do the same to every segment of the new figure. Each segment is replaced by 4 smaller ones. Then again forever. At every stage, the boundary becomes more intricate. Small triangular protrusions appear everywhere. What was once simple becomes serrated, then highly serrated, then impossibly detailed. The edge never smooths out. It does not approach a classical curve in the ordinary sense. Instead, it acquires finer and finer irregularity. The important thing is that the rule is simple. Each segment is treated in the same way. Recursion is at work again. A single local instruction, repeated endlessly, creates global complexity. And this is a common theme in fractal geometry. The richness of the final object does not come from a complicated recipe. Often the recipe is almost childlike in its simplicity. The complexity comes from iteration. It comes from the fact that the rule is applied again and again without end. Now the Koch snowflake has a famous and wonderfully unsettling property. It encloses a finite area, but its perimeter is infinite. The interior remains bounded. The figure does not spread out to cover the whole plane. The amount of area added at each stage becomes smaller and smaller in a controlled way, so the total enclosed area converges to a finite limit. But the boundary length behaves differently. At each stage, the perimeter increases by a fixed multiplicative factor. The total boundary keeps growing, and it never settles to a finite value. It diverges without bound. So here we meet another fractal paradox. The shape surrounds only a finite amount of area, and yet to walk along its edge would require an infinite journey. That is an extraordinary statement. It tells us that inside a bounded region, within a figure that does not grow outward without limit, one can still hide an endless amount of boundary. Infinity can be packed into the edge. Let us pause and reflect again. In ordinary geometry, we grow accustomed to a certain harmony between length and area. Larger boundaries often enclose larger regions. Smooth curves behave in ways that support our intuition. But fractals teach us that these expectations are not universal. Under recursive refinement, the boundary can become infinitely elaborate while the enclosed area remains controlled. This does not destroy geometry. It deepens it. It tells us that our naive intuitions were formed in a narrow class of shapes, mostly smooth and regular ones. Once irregularity enters in a systematic way, geometry becomes more subtle. And that is one of Mandelbrot's great contributions, as we shall later mention more directly. He helped reveal that roughness itself could be studied rigorously, not as a defect, not as a failure of geometry, but as a legitimate and central mathematical phenomenon. Before reaching Mandelbrot, however, let us consider a third classic fractal, the Sierpiński triangle. Once again we begin with an equilateral triangle. This time, divide it into 4 smaller congruent triangles by connecting the midpoints of the sides. Then remove the central triangle, leaving behind 3 corner triangles. Now repeat the process on each surviving corner triangle. Remove the center from each. Then repeat again on each of the smaller survivors. And so on forever. The visual result is hauntingly beautiful. More and more holes appear. A lace-like pattern emerges. Triangles contain smaller triangles, and the empty spaces themselves form a repeated structure. It feels balanced and airy, ordered and hollow at the same time. The Sierpiński triangle is a lovely example of recursive emptiness. More and more material is removed, and yet the remaining structure remains sharply organized. It does not dissolve into randomness. Quite the opposite. As more is taken away, the pattern becomes more articulate. This is another important lesson of fractals. Repetition can preserve form even under relentless reduction. Order can survive subtraction. Structure can become clearer, not less clear, as pieces are removed. The Sierpiński triangle also reinforces a general theme we have already seen with the Cantor set. Infinity is often expressed not by adding endlessly, but by repeating a rule of refinement. The object is not infinite because it stretches forever in space. It is infinite because its structure can be examined forever in depth. And that phrase may be the most important one in this entire discussion. Fractals contain an endless depth of structure. That is why they feel so different from ordinary finite figures. With a classical triangle, there is only so much to say geometrically once the shape is given. But with a fractal triangle, every closer inspection reveals a new stage of the same governing idea. The object contains a recursive interior life. Now, as mathematicians reflected on such objects, a very natural question arose. What dimension do these sets have? In school geometry, we are taught a simple hierarchy. A point has dimension 0. A line has dimension 1. A surface has dimension 2. A solid has dimension 3. These are clear and stable categories, and for ordinary smooth objects they work beautifully. But fractals begin to blur these categories. The Cantor set lies on a line, but it is not like an ordinary interval. It is too scattered to behave like a one-dimensional segment. Yet it is certainly more than a finite or countable collection of isolated points. The Koch curve is more elaborate than a smooth curve, almost as if it tries to spread into the plane without ever becoming a filled region. The Sierpiński triangle lives in the plane, but it is too perforated, too empty, to behave like an ordinary two-dimensional region. So one begins to feel that these objects sit somewhere between the familiar dimensions. Not literally between them in physical space, but between them in the way they scale, in the way their complexity changes under magnification. This leads to the idea of fractal dimension. Fractal dimension is a way of measuring how the complexity of a set grows as we examine it at finer and finer resolution. If a set were a simple line, its scaling behavior would match what we expect from a one-dimensional object. If it were a full region in the plane, its scaling behavior would match a two-dimensional object. But a fractal may scale in an intermediate way. It may behave as though it lies between 1 and 2 dimensions, or between 2 and 3. This is a profound conceptual expansion of geometry. Geometry is no longer limited to points, lines, surfaces, and solids as completely separate boxes. There are also objects that inhabit the spaces between these categories, not physically in the everyday sense, but mathematically in the sense of scaling and complexity. It is worth repeating that carefully. Fractals teach us that dimension can be more flexible than the whole numbers suggest. That flexibility is made rigorous by notions such as Hausdorff dimension. Now, we do not need technical machinery here, and it is better for our present purpose to remain intuitive. But the basic idea is very beautiful. Hausdorff dimension asks, in a refined way, how a set behaves when we try to cover it by very small pieces. As the pieces become smaller and smaller, how does the amount of covering needed scale? What exponent best captures the set's geometric complexity at arbitrarily fine resolution? That question allows mathematics to assign non-whole number dimensions to highly irregular sets. In that sense, Hausdorff dimension gives precision to the vague feeling that certain fractals live between dimensions. The main point is conceptual rather than technical. Fractals force geometry to become subtler. The classical language of dimension is not abandoned, but it is refined. Mathematics becomes capable of describing forms that classical geometry could see but not fully measure. Let us pause and reflect once more. We have seen three major examples. The Cantor set shows us a set that is uncountable, closed, nowhere dense, and of measure zero. The Koch snowflake shows us a figure with finite area and infinite perimeter. The Sierpiński triangle shows us a recursive pattern of emptiness, order, and nested holes. These are not isolated oddities. They are different expressions of the same deeper theme. Simple, repeated rules can generate objects of endless detail and surprising geometric behavior. And this is why fractals feel both natural and uncanny. They feel natural because the world around us is full of roughness, branching, layering, and irregularity. Consider clouds. They do not have the clean boundary of a sphere. Consider a fern. One leaflet resembles the whole plant. Consider a tree. The trunk divides into branches, the branches into smaller branches, and the branching logic repeats. Consider Romanesco broccoli, whose spirals seem to reappear in smaller spirals, preserving the same visual idea across scale. Nature is rarely exactly self-similar. A real tree is not a perfect mathematical recursion. A coastline does not repeat itself with absolute fidelity. But many natural forms show approximate a statistical self-similarity. Their structure is not identical across scales, but it is related across scales. That is enough to create the powerful emotional effect we associate with fractals. They seem to stand halfway between strict mathematical law and living, organic form. Perhaps that is part of why they are so compelling. They are rigorous enough to study and wild enough to feel alive. Fractal geometry gives us a language for roughness. It gives us a language for branching. It gives us a language for patterns that are neither smooth nor random, but recursively organized. And in the 20th century, one mathematician above all helped make this perspective visible to a wide audience, Benoit Mandelbrot. Mandelbrot did not invent all fractals, of course. Many classical examples were known long before him. But he played a central role in unifying them conceptually and showing that irregular shapes deserved serious mathematical attention. He helped popularize the very word fractal. He emphasized that roughness, jaggedness, and complexity were not merely pathological edge cases to be dismissed. They were central features of the world and worthy objects of study. This was a major shift in mathematical sensibility. For a long time, much of classical geometry and analysis focused on smooth curves than well-behaved surfaces. Fractal geometry broadened the conversation. It showed that irregular forms could have their own laws, their own dimensions, their own elegant structure. Many fractals, including some of the most famous ones, arise not from geometric cutting and replacing, but from iterative math in dynamical systems. A simple transformation is applied repeatedly, and astonishing patterns emerge from the long-term behavior. So fractals are connected not only to geometry, but also to dynamics, to iteration, to the study of how simple rules generate complexity over time. Again we return to the same great theme. Repeat a simple rule often enough, and infinity begins to appear. Now let us gather the main ideas together slowly. In the Cantor set, infinity is hidden in endless deletion and survival. Infinitely many stages of removal produce a set that is thin in measure but large in cardinality. In the Koch snowflake, infinity is hidden in the edge. The boundary length grows without bound, even while the enclosed area remains finite. In the Sierpiński triangle, infinity is hidden in nested emptiness. The holes multiply, yet the structure retains its coherence. In all three cases, infinity is not merely a matter of having infinitely many points. That is true, but it is not the most vivid truth. The deeper truth is that these objects possess endless depth of structure. Under magnification, more can always be said. Under further refinement, the same rule still speaks. That is why fractals make infinity visible. In set theory, infinity may be visible through size and correspondence. In analysis, infinity may be visible through limits and convergence. In fractal geometry, infinity becomes visible in shape. This is the third major language for the infinite. And it is perhaps one of the most intuitive once the eye becomes accustomed to it, because it speaks directly to perception. We can almost see what it means for a shape never to finish unfolding. Let us pause and reflect one last time. A fractal is not just a fancy picture. It is a disciplined expression of recursion. It is a geometric limit of repeated finite stages. It often displays self-similarity, meaning that the whole resembles its parts. It reveals new structure at every scale. It challenges our old intuitions about length, area, dimension, and size. And it teaches us that mathematics can describe forms that are rough, delicate, sparse, intricate, and infinitely deep all at once. The Cantor set teaches that a set may be uncountable and yet have measure 0. The Koch snowflake teaches that a shape may enclose a finite area while having an infinite perimeter. The Sierpiński triangle teaches that removal can create structure and that emptiness can be patterned. Fractal dimension teaches that geometry need not be confined to whole numbered categories. Hausdorff dimension gives that insight rigorous form. Nature reminds us that these ideas are not merely abstract. Branches, clouds, coastlines, and ferns all whisper something fractal to us, even if imperfectly. So as we come to the end, let us gather everything into one calm thought. Fractals show us that infinity is not only about endless counting and not only about endless processes unfolding in time. Infinity can also be folded into shape itself. A form can contain infinite refinement. A boundary can hide endless length. A set can be everywhere delicate and still immeasurably rich. A rule can be simple, and yet what it generates can be inexhaustible. And perhaps that is the deepest quiet lesson here. The infinite is not always remote. Sometimes it appears in the small. Sometimes it appears when we look closer. Sometimes it appears in a coastline, a branching fern, a cloud, a snowflake, or a triangle from which pieces are endlessly removed. And so fractals invite us to look again, more patiently, and then more patiently still. What seemed irregular becomes structured. What seemed chaotic becomes recursive. What seemed merely decorative becomes profound. Under magnification, the world does not always become simpler. Sometimes it becomes deeper. Sometimes it becomes stranger. Sometimes it becomes mathematically beautiful. And sometimes, in that beauty, we catch one more glimpse of infinity.